I'm Cade.
I'm Emily.
I'm Ryan.
And this is Lab 10 Imaging System Calibration.
To measure the camera's pixel size, we used a microscope on a micrometer translation stage to take horizontal and vertical measurements of the sensor, and then we looked up how many pixels there were per dimension so that we could calculate the size of each pixel. So we got 5.31 microns for each pixel size, and the datasheet for the camera says 5.3.
In order to measure the field of view of the camera, the target was placed on the opposite end of the table from the camera. The target filled the frame of the camera, and we marked the positions that match the edge of the field of the camera. The distance from the target to the camera is marked as the distance z, and the distances x and y correspond to the horizontal or vertical edges of the target that filled the camera's frame. From here, the half and full fields of view can be calculated by taking the inverse tangent of half of the distance in the horizontal or vertical direction and dividing that by the distance from the camera to the target. The ideal calculation for the full field of view will have the entrance pupil to the target, but since we don't know where that entrance pupil is, we had to approximate that with the camera post distance to the target. The vertical full field of view was 11.91 degrees and the horizontal full field of view was 14.85 degrees.
At least 20 pictures were taken both for the fisheye lens and for the regular lens. You need at least 15 to 20 pictures because there are 9 degrees of freedom that your system is trying to solve for between the focal length, principal planes, and the different distortion values. So for the procedure for setting up how to find the distortion for each photo, you go to Extract, Image Corners, and then you just hit Enter to have all of your images processed. Then you need to select the 4 different corners in between the junctures on the crosshair board. And then once you get this, it asks for how many boxes are in each direction. And then as you look at the red crosshairs that it tries to put on the checkerboard, you see that they're a little off. So you need to guess for some initial distortion, this K sub C factor, and with a good guess, those red crosshairs move onto your corners. So for each of the different images, you need to orient the checkerboard in a different direction. Here you can see one of the setups that we have at the end of all these different directions and orientations of the checkerboard allows you to completely reconstruct the image distortion for your system. These different orientations and positions of the checkerboard correspond to our extrinsic parameters of the system. We're then able to find the intrinsic parameters of the fisheye lens using this method, and we're able to use this function called recombine corners in the GUI to decrease our pixel error from about 1.6 to about 0.35. This function works to really precisely measure where exactly the corners are, because when we just click in the windows when we're selecting things, there's about a 5 pixel error radius, and this one decreases that significantly. The MATLAB program gives us a set of intrinsic parameters for the lens system. So for this lens with low distortion, it gives us the focal length, principal points, and these different distortion values corresponding to different directions. And for the low distortion lens, we found a pixel error of about a half pixel.
So MTF is a measure of how well an optical system can reproduce details from your object to your image as a function of how large a feature on your object is. So when we measure MTF, we expect to see a graph like this, where on your y-axis you're comparing the contrast of the image over the contrast of the object as a function of spatial frequency, and we're comparing our actual curve to our diffraction limit, which would be in a perfect system. The ideal way to measure MTF is with a target with a slant diagram on it. This is because if you have rectangles that are with perfectly vertical edges, you'll get two, either best case or worst case MTFs, neither of which is perfectly representative of your optical system. So the best case is that the edge of your rectangle will fall perfectly between 2 pixels, and the worst case is that the edge will fall in the middle of a pixel. So those MTFs, neither of them are actually representative of your optical system. Whereas with about a 5-degree slant, you can take the MTF over that edge and it's much more representative of what your optical system, how it's performing.